Class is now starting. All attendees are in listen-only mode.
Okay, well, I've got 2 o'clock Eastern time. You're on the Getting the Most Out of Your Blower Door System webinar with Retrotec. So we'll go ahead and get this started. So just to begin with, right now you should hear me talking. So check your audio. If not, make sure you've got everything on and active. We use our question box. So if you have any questions coming up, we are fielding questions in the background. So feel free to ask anything that comes up that's not really clear. If you want some more on, we'll stop about halfway through and take questions, and we'll take some more questions at the end. And feel free to make any comments. Let us know how we're doing. So for Retrotec webinars, you get 1 BPI CEU per webinar. So you got to make sure that you're paying attention, and make sure you give us your full name, your email address, and your BPI member ID number. And it's important that you are active and paying attention, because we can tell if you're not, and if you're not, BPI won't let us give you that CEU. So just make sure you're active and paying attention and staying attention to everything. So one thing to mention is that we do have our trade-in program still going on. So if you want to upgrade to a DM32 smart gauge and you have a DG700, you can trade that into us. Right now, our DM32 gauge runs at $1,450 with Wi-Fi, but if you trade in your DG700, you can get it for $995, and that comes with an adapter to use with your Minneapolis fans. So we'll go ahead and get the ball rolling here on getting the most out of your blower door system. So in the residential testing industry, blower doors are typically used in HERS ratings and energy audits to get a leakage number to see how severe that leakage is in a home. But you can also use your blower door for other diagnostic tools to find out where that leakage is coming from. And so we're going to go through some different methods today on how to do that. And just to introduce myself here, I'm Sam Myers. Oh, sorry, here we go. I'm Sam Myers. I'm a trainer with Retrotec. I've conducted a lot of blower door and duct tests in the field. I'm a certified ResNet HERS rater. Formerly, I was a building science specialist at Advanced Energy, located here in Raleigh, North Carolina. And I've trained a lot of contractors and HERS raters on how to do some of these things that we're talking about today. And I'd like to introduce a special guest that we have with us today, Mr. Jay Bowen. Jay specializes in thermal imaging, and this is the second time we've given this webinar this week. So, Jay, thank you for joining us again, and I'll let you introduce yourself here.
Thanks, Sam. As you can see, I've pretty much started my career as an electrician, but I became a thermographer, went on to become an ASNT level 3 thermographer, which pretty much means I can do the training and program development type of activities, but my real forte is on the training side, and being out and doing on the building side especially is kind of a passion of mine. So I've designed number of different building classes, building specific classes, and ultimately it's how Sam and I met at a conference where I was teaching folks how to do blower door testing in a clinic. So Sam and I got together with this one, and we can bring you some good knowledge and good technology in a short amount of time today. So again, thank you, Sam, and I'll look forward to having my part as we get through this.
Great, thank you, Jay. And just to go ahead and warn everybody, we have an hour blocked off for this, but we have a lot of content packed in. And so Tuesday we went over an hour, and so this is probably going to happen again today. So if you have to cut out early, that's fine. We understand, but we will have this posted on YouTube, on our YouTube channel in a couple of weeks. So just to let you know. So with these webinars, I understand that there's usually a lot of people that join these that are new to the industry, new to diagnostic testing. And so before we really get into the weeds of different types of testing, I like to just start out at the beginning, talk about air tightness, where some of the issues typically occur, and basically how a blower door works, basic mechanics and things such as that. And so we'll go ahead and start off kind of at the beginning, and then we'll get into some different test methods. So why do we test? Why do we run a blower door? Typically for code or quality assurance or quality control. Usually, depending on what state you're in, your code may require that, or maybe the homeowner would want it if it's not required, just to make sure that the quality of the construction is going to be top notch. Also, we like to breathe clean air. This is a mock-up we had at a conference. That's Larry Zarker, who heads up BPI. That's just a little model that we made to show that the kind of contents that accumulates in a wall cavity over time in a leaky home. So as air comes in from outside, typically it picks up stuff in the inside of the wall cavities too before it hits your nose, mouth, and lungs. So for envelope tightness and leakiness, this can occur different ways. A lot of people think that it's all around doors and windows, but really it's through your floors, walls, and ceiling where different building materials meet. So that makes up about a third of it. If you look at this graph, ducts are another part of it. Your duct system is actually a part of your building envelope, believe it or not. And fireplaces are also a big one, as well as penetrations through the shell, such as plumbing penetrations, wiring, and then of course doors and windows are a part of it too. And air leakage is a big cause of high energy bills. We know that, as well as comfort issues. But one of the biggest things, in my opinion, is indoor air quality. Because the quality of the air that we breathe is really important. And if you live in a humid climate like I do, it also causes durability problems, especially if you have moisture that's getting trapped in a wall cavity and it has nowhere to go, then it condenses, and that can rot out framing members, which will cause things to deteriorate down the road. So let's talk about air barriers. This little drawing here represents an existing home. So your air barrier is made up, can be defined different ways, but in an existing home, it's typically made up of your floor, your drywall at your ceiling, and usually it's your drywall on the inside, especially if you're doing a retrofit, because if you're leaving the drywall in when you're doing your retrofit, and there's really not much you can do with your wall assembly. So you want to seal up that drywall the best you can. And so typically you seal up around receptacles. And then from the ceiling side, everywhere you have a penetration, such as an electrical box or a can light, and definitely your duct system, where return boxes and duct boots penetrate through the ceiling, and then the ducts themselves. And so this model just kind of shows where air leaks through the building envelope and how it behaves. In the middle here, you can see this arrow going through. So that would be like a plumbing penetration where air would leak through the wall. And plus you have your thermal boundary and your air barrier, and you typically want your air barrier aligned with your thermal boundary, which is where your insulation exists. So you want your insulation to be in contact with your air barrier. And so this sectional drawing here really represents how you would have your air barrier aligned properly in a new construction home. So that's when you're incorporating air barrier into the design as you're building. So here you can see we have it aligned on the sheathing. And that's really the best place because you have less penetrations than you do in your drywall. And you just have much more control of how you can stop air coming in, caulking different framing members, caulking sheathing to framing, caulking around penetrations. And you can follow it up to see where your critical ceiling parts are, especially as you get to corners. Corners are always weak spots. And this is a drawing from Advanced Energy's System Vision program. So when I was working with this, a lot of times when I was training builders in a classroom setting, I would hand this drawing out to my students and have them draw the air barrier themselves to guess where it would make the most sense. So that was usually a pretty good exercise. And then we also had the critical ceiling points on the ceiling as well. If I were to change one thing about this drawing, it would have the air barrier to actually incorporate the duct itself and not just go over it, because ducts are part of the envelope. So that's an important thing to remember. But where your sheetrock meets top plates and bottom plates, that's important as well, because that'll stop attic air from coming into that wall cavity, or conditioned air in that wall cavity escaping into the attic area. So these are just some pictures to show different penetrations. If you were to walk on a new home at the framing stage, so you can see this plumbing penetration that would need to get sealed up with caulk or spray foam. Same for wiring penetrations here. gaps above windows, or anytime you have a framing member meeting another, holes cut out for electrical boxes or receptacles. And then the stud pack here is another prime example. You can see where they sealed it up some, but here you have some daylight peeking through. So if you're walking through a new home at framing stage and it has the sheeting on it and it's ready to go and you can see daylight, there still needs to be some air sealing done. So what I was mentioning before about top plates, so this is in an attic looking down at the top of a wall. And so you have a crack here on the side, on both sides of your wall. So this is an interior wall. And this is true for both interior and exterior walls. And so on new construction, before the sheetrock goes up, what a lot of contractors do is they tape up seal, which is like a thin foam strip that you can staple to the side of the top plate. And then that creates a gasket between the top plate and the ceiling. And a way to test to see if it's there, if you can't see it, you can take a piece of paper or cardboard and try to slide it through. If you can get it through, then you have an air leak. And if you were to retrofit this problem, you can use spray foam or caulk. You can even use bucket mastic, but here they use some spray foam to seal up those top plates. Chases are another big one. So in this house, they have just an empty void area. They were either this is either just a dead space on the plans, or they were gonna run some ductwork through here and then decided not to. So you have this empty or this uncovered chase here. So that's like having a window open all the time in the worst possible place because it's bottom or bottom to top. So you want to cap that with a rigid material such as plywood. And then what's missing here is sealing around the edge with either caulk or spray foam. And like I said before, corners are also weak spots where your sheathing meets. So you have a gap here or a crack behind these studs. They did a good job of sealing this bottom plate to the subfloor, but where this sheathing meets this corner stud, you would want to seal there. And this is a 2-stud corner. There's a stud back behind here you can't see. This is just a nailer. And so back behind this stud, you would want to seal back there as well, where that piece of sheathing meets the stud. And the more corners you have on a home, the more it's going to leak if they're not sealed up. So this is a good air sealing detail around a window. This is low expansion foam. This white foam is really good stuff to use because it doesn't expand really hard or really far out like a fire block foam does. You never want to use the pink fire block foam on this because it'll expand too much and then it can deform the windows. But this looks like a really good job here. And then this is a return box in a ceiling. So imagine if you're on a ladder and you're sticking your head up into the return box, this is what you would see. And so this gap here between the sheetrock and the return box is a really critical air sealing detail, both for your duct system and for your building envelope. And so you would want to hit this up here with some caulk to seal that gap all the way around. And the same goes for the supplies, the supply registers as well. Recess lighting is another one that typically pops up. They went and sealed around this here, but even if you have airtight can lights, they still leak some. So what some contractors do, you can build a box out of plywood or drywall to put over it that's air sealed and then seal around it. And some building material manufacturers also make housings just for can lights for that same scenario. So that was just a quick rundown on air sealing, some of the typical spots that we run into in the field that need to be sealed, why it's important. So now we'll look at a blower door, how it works, and why we use this for testing air leaks in buildings. So just some basic mechanics of how a blower door works. Air flows across a sensor in the center of the fan, which is what this arrow is pointing to here. Your manometer then is able to read the pressure and calculate the flow. So as long as you have pressure and a known opening, which the manometer knows the opening of the fan, the manometer can then calculate the flow and convert it to CFM. And then if you, on this specific manometer on the DM32, you can enter the volume of the building that you're testing, and it can then give you ACH instantly as you're testing. That way you know you've passed or you've failed your whatever target you're looking for. So just a closer look at the pressure, the sensors on the center of the fan. You have these 4 ports around the center of the fan. This yellow piece is called the nacelle, and that's where the air is collected and then read by the gauge. So these ports are connected by tubes that then eventually connect to the top of the fan where your hose plugs into, that then plugs into the gauge. So that's how it all connects. And so in residential buildings, the standard is to either pressurize or depressurize the house to 50 pascals. And so in this scenario, we are depressurizing the home. And so these arrows are simulating air getting pulled out of the home. These dark blue arrows are air getting pulled into the home from the outside. And so when we set up our blower door, we have a reference hose that runs from the gauge through the shroud here to the outside, and that's our reference line. So that's going to read 0, and then the gauge itself on the inside is going to read negative 50 pascal. And then anywhere along the shell where air is leaking in is going to read plus 50. So this is just a little simulation to show how depressurizing a house works, where the air comes in from, how the blower door reads it. These red arrows are infiltration coming in. So basically what it does is it amplifies the infiltration of the house at a certain pressure, which is 50 pascal. So that way it can know how bad it's leaking. And so this is looking at the difference between depressurization and pressurization. For most standards, both are acceptable. But one thing we recommend, if you have the choice, we recommend doing depressurization, because on the envelope of your house, you have different dampers that go to various things, such as your bath fans, your kitchen exhaust, dryers. And so if you do pressurization, like this damper here, it can blow those out and give you a higher leakage number. And for most standards, you're not allowed to go around and tape these kinds of things off. So if you do depressurization, it'll pull them shut to give you a tighter number. So what does this mean for HVAC contractors? Typically when we think blower doors, we think HERS raters and BPI people and energy auditors, but this is a big deal for HVAC contractors as well, especially for those of you that are familiar with doing HVAC load calculations. So if you're familiar with those type of calculations and the software involved, such as RightSoft or Elite, you have to enter in your infiltration of what the house is going to be. And a lot of times people just wing it. They say it's average. You have choices from terms such as loose or tight or semi-loose or semi-tight. And without actually testing the envelope, you really don't know what you have. And on this load calc software, you have the ability to go in and enter a blower door number. And so if you can enter that blower door number in, then your infiltration is going to be correct. There's no variance that's going to affect the sizing. So infiltration can be 15, sometimes 20% of the load, depending on how leaky that house is. And so when we're talking about tight, semi-tight, average, that's how these numbers relate. So we're talking 4 ACH for average. I mean, I would say that's a little more on the tighter side than your average home, code-built home that you're going to see. If someone just assumes that it's tight, well, as far as concerned, that's 1 ACH 50. That's really tight. And passive house is 0.6, so that's getting in that neighborhood. And then loose is 8 ACH 50. Some existing homes, older homes might even be more loose than that. And so that's when it's going to be really important to actually enter in that correct number from a blower door test. And so sometimes we get the question of when is the house too tight? Well, you can't get it too tight. You can get it as tight as you want to. You can get it as tight as you can. The difference is when do I need ventilation? Because before we relied on this unplanned air coming into the house, and that was our ventilation. It just kind of came in from wherever. Now that we've sealed all that off, we still need to ventilate. We need to have clean air coming in, because the air in our homes gets stale after a while. Moisture can't get out, and so usually at 5 ACH 50, that's when we want to bring in some outdoor air from mechanical ventilation. And that's going to be from a device such as an ERV or an HRV, or positively pressurized ventilation, such as an air cycler fan, something such as that. So who can do a blower door test? Well, in a lot of codes, really what you need to look at is, if you're just doing it for code, you need to see what the local code says. But typically it's just about anybody. The GC can do it, the insulator can do it, HVAC contractors are usually allowed to test it. They're even allowed to do duct tests on their own work in most cases. The builder can do it, pest control. Sometimes the permit owner can do it, or the homeowner can do it. Really, whoever the building official gives authority to. So that's kind of the basics of why we do blower door tests, how they work, who they benefit. Now we'll look at some different methods that you can add into your blower door test to make things faster, to be able to identify problems, things such as that. So now we'll look at some different apps that are out there that Retrotec has created to make life a little easier in the field. So you've probably heard us talk about rCloud before if you've attended some of our webinars. It may be new to some of you, so I'll introduce it. Basically what this does, it's an automated testing app. So your DM32 gauge gives off a Wi-Fi signal that you can attach to your device, whether it's your phone or a tablet. And what this does is you can run your fan off your device, and not only that, it'll geolocate where you are. If it's new construction, then you can say, hey, this is new construction. It'll pull local weather data to go ahead and get your outdoor temps. And you can choose what standards you're testing to. So if you're a HERS rater, you can say, I'm testing to the ResNet 380 standard. And it'll go ahead and pull that up. And once you run your test, you can choose, or before you run your test, you can choose whether you're doing a single point or a multi-point test. And this is where the big difference is, because before this type of technology was out, it was nearly impossible to run a proper multi-point test in the field without having to do a bunch of extra math. And so now this does all that for you. You know when to change rings, you can pause the test, adjust your ring setup or your range plug setup, and then resume the test. And so now this makes multi-point tests really easy. And for those of you that have been paying attention to ResNet 380, if you do a single point blower door test, you have to take a 10% penalty if you're registering that in the ResNet registry. So with a multi-point test, you don't have to worry about that. And that's why this makes this so much easier. And you can be connected to the internet. Once you run your test, if you're connected to the internet, it's going to give you a nice report, and then you can share that with yourself or with the building official or with your employer or with the homeowner, whoever. You can just email it out right off your device right after you run the test. If you don't have internet, still works just fine. It'll save all your data. Once you get back to your home or office, wherever you have an internet connection, just open up the app again, and it'll send that to the cloud so that you can see how the home performed and then share the results. So it works on both phones and tablets for both Apple and Android. And it even run off your Windows PC as well. And the nice thing about this is it gives you a nice report at the end of it. It shows you where you were, the address, characteristics of the house, such as the volume and square footage, what the outdoor temperature was. When you go in and set up the house, you have to manually put in the indoor temperature. And it'll tell you, depending on what your target is, you manually set your target on whatever leakage you're looking for. And at the top, it'll tell you if you passed or failed. So this is really nice to leave with a building official or send to your HERS provider. Your HERS provider loves this. And so another app that we have available that makes life a little easier is the Gauge Remote app. And basically what this does is it mirrors the screen on your gauge to your device, whether it's your phone or tablet. That way you're free to walk around the house and control your fan from anywhere in the house. So if you want to have your phone in one hand to control the fan and a smoker in the other to find leaks, or your phone in one hand and a thermal imaging camera on the other to walk around and control the fan without having to run back and forth or have a second person, this makes things a lot faster. It's also really handy for duct testing, especially if you have your duct tester set up in the conditioned space and then your air handler's up in an attic or down in a crawl space. This allows you to go check for leaks without having to have a second person or run back and forth to the tester and the air handler. Virtual Gauge, this isn't really a device app. This is a program that you can download and have on your PC. So this does something similar to what Gauge Remote does, but it puts the screen of the gauge on your PC. So it's really nice to share with customers. If you carry your laptop into the field, you can go ahead and pull up the gauge from the kitchen if you want to sit down with them and not have to be at the fan and show them what's going on and explain things. It's also really good for training. So if you're like me and you train a lot of people, it's great to go ahead and pull this up on a big projector and then explain what's going on as things are changing on the gauge. That way everybody can see it. So that was apps, and so now we'll talk a little bit about whole house ventilation. And I know this is kind of a random topic to throw in, but you can actually use your blower door to verify if certain types of whole house ventilation are working properly. And the type that I'm referring to is positively pressurized ventilation. And so that's going to be like your ASHRAE 6022, where you have an air cycler fan and a motorized damper that ties into your return system. So this is the one that Honeywell makes. This is just an example. There's several different ones out there. April Air makes one. Air Cycler is another brand that makes one. But basically what this does is that you have a ventilation duct that ties into the return side of the system. A lot of the times it's on the return box, so that way it can be filtered from the inside. Other times it'll be on the return trunk line or on the plenum and then be filtered from the outside. It is important that it is filtered somewhere and that the homeowner can get to it. So that's one thing to look for, but to check to see if it's working, it's just a picture of the inside of the return box with the filter on it, just to give you an idea of what this looks like in the field. But to check to see if it's working, this is what we refer to as the Tooley chart. This is just what the common name of this chart. John Tooley is a well-known building science expert in the U.S., and he's the one that really introduced this chart to the industry a while back. But it looks like there's a lot going on here, but this is actually pretty easy to use. And this works really well for smaller or tighter homes. And basically how this works is on this x-axis at the bottom, this is going to be your blower door number. And so that's the number you're already going to know. On this y-axis, that's going to be the airflow of the ventilation system. And the way the two meet, what's important up here at the top is this key. And so this is in pascals. And so these increments is the pressure difference between just the air handler fan running by itself and then the air handler fan running with ventilation on. And so what you do is you turn the air handler fan on, no heating or cooling, just have the fan running, have the ventilation damper shut or taped off, and then you have your manometer reading the indoor pressure with respect to outside. And then you'll stop the test, record your reading, and then you'll run it again with the ventilation damper open, and it should be a positive difference because you're bringing air into the house, and and with a positively pressurized system, you don't have any way to exhaust stale air. It's just bringing new air in. And so it should be a little bit more positive. And so say you have a pressure difference of 1 and your blower door number is 1,000. Okay, so 1 is this orange line, 1,000 is here. And so if we run it over to this y-axis, that's telling us that our ventilation system is bringing in about 78 CFM. So it's not a ResNet or BPI approved way of measuring ventilation, but it is a way to check and see if it is working if you can't really get to it. For example, if you have a 2-story home built on a slab and it has one system and it's up in the attic and they ran the ventilation out to the gable end, it's going to be really high off the ground and you're probably not going to have a ladder to get to it. But at least this way you can check and see if it's working. So on the last webinar, we had people request this. I do have this on a PDF with some instructions on how to use it. If you want it, just go in the question box and let us know and we can send it out to you. But it's probably not something you're going to use a lot in the field, but it is good to know that it's there. So I mentioned smoke testing before. I'm just going to show a couple of devices that are out now to show how smokers have evolved for the field. We used to have the titanium tetrachloride puffers Those are really toxic to breathe in, and it's not good for metal components. And so one thing that we have out now is this handheld fog machine. It's called the Tiny S. It's made by Look Solutions. Retrotec distributes it. You can get it from us. And it comes in this nice case, and it's basically a vaporizer. You fill it with this fluid. You fill these cartridges up with the fluid, and they just pop in. Comes with 2 rechargeable batteries. Fits in the palm of your hand. You press the button. A big plume of vapor comes out that behaves just like smoke, and it hangs nicely in the air. And so it's really good for going around and checking penetrations to see how that air is behaving with the blower door running or with a duct tester running. So this is a small clip that I took. I went out with a company to a new dormitory building that was being built at VCU in Richmond, Virginia. We did a 17-fan test, blower door test on this building. And we went up to the top floor just to try to find some penetrations in the roof. And so you see a ceiling here, but the air barrier is actually on the roof deck. And so it should be airtight underneath this, or above this ceiling here. We were depressurizing the building, and we had the Tiny S running. And so you can see there's a significant leak there coming out of that access panel. And then we went over to a light fixture. So this section of roof had an air leak that was pretty significant. So that was a quick and easy way to find that out. A lot of times you can feel it with your hand, but a lot of times you can't. And so if you put a smoke detector, this one's really, or not a smoke detector, but a smoker like this, it's really quick and easy way to find them. And so the Tiny S has a big brother called the Power Tiny. So this is a bigger fog machine that you can actually use to fill up a room or sometimes a whole house, and definitely a duct system. And that way you can either step outside and see where the leaks are coming from, or you can run your blower door and follow the smoke inside to see where it's escaping. And just for reference, we have a clip discharging it outside, so it puts out a whole lot of vapor. And it's odorless. I mean, it's not smoke, it's vapor, so it doesn't leave an odor or anything in the house. Once it's all out, you can't even really tell that it was there. So that was just a quick tidbit on smoke testing and just some things that are out there and how you can use it. Now I'll talk about zonal pressure diagnostics. And when we talk about zones, we're really talking about how to find leaks between conditioned space and unconditioned space. So that's going to be looking at leaks between your conditioned area and a crawl space, or the conditioned area in the attic, or an adjacent garage, or an adjacent storage room that's built onto the side of the house, and try to locate to see where those leaks are coming from. So this is a model house that we use for this demo, just for these webinars. And so basically how you do this kind of test is you depressurize the house to 50 Pascal, just as if you were going to test it. And then you detach your manometer so that it's no longer connected to the blower door, so that you're still depressurizing to 50, but the manometer is going to read 0. And so your manometer is going to say it's 0 inside. And so that means it's going to be positive 50 outside. So that way, once you reference to other spots, so if you're going to reference an attic, which can be a little tricky to do sometimes because you want the attic to still be closed off, but you want to get a hose through there. There's ways you can do that by using, you can go to places like Hobby Lobby and get some small copper tubing with hoses and adapters to allow you to do that. And I have a slide later on that shows you what that looks like. But you would reference the indoor space to the attic and see how the air communicates with each other between the two spaces. So if it's more 50 than it is 0, that means it's going to be more outside than it is inside, which means it's going to be leaky. So if you have a ventilated attic and you're getting 20 Pascal, I mean, it's closer to inside than outside, but it's still kind of leaky. There's still some areas in there you would want to look at. And, it could also mean that the attic vents need to be a little bigger, that the attic isn't getting enough ventilation. So it's important to look at both and figure out why you're getting that reading. For a sealed attic, if you have spray foam, this is a good way to see if that spray foam on the roof deck is really working the way it's supposed to prevent infiltration. So if you do the same thing, if you close it off, or this way you would have your attic hatch open. If you're getting 2 with respect to inside, I'm sorry, you would have the attic hatch closed. If it's reading about the same, close to 0, so if you get 2 instead of 0, that's really close. That means that spray foam is doing a really good job. And then the same for crawl space. Crawl space, sometimes it can be a little tricky to get something down there, kind of like with attics. If you have ducts in the floor, if it's an existing home, you can pull up the register. Sometimes you can get a gap between the supply boot and the floor to put a hose down there. Sometimes there's an access hatch to get into the crawl space. But if you don't have those two options, you can then run a hose outside and then come back into a crawl space vent or through the crawl space door. But one important thing to remember is that if you run hoses outside, you want to keep them out of sunlight. Heat from sunlight will affect your reading. And a little tip for that is if you have to get in sunlight a little bit, using a red hose will block out heat from UV better than any other color. So just a little tip there, but try to stay out of the, and that's the same too for your reference hose for your blower doors. Always want to try to keep those in the shade. And so here's what I was talking about too with tubing, how you can get different sizes. So you can get smaller size tubing. That way you can bend it and manipulate it in different ways to make it so you can get it around that attic hatch so that it'll, if you have weather stripping around your attic hatch, that way it'll sit in it and not push the hatch up or down. It's nice too with the smaller tubing because you can also get underneath baseboards. You can get in other smaller holes. Just don't poke holes with it through caulking like this or it'll clog it up. You always want to check it with these smaller tubing just to make sure you don't have a clog in there that's going to affect your reading. So pressure pan diagnostics is a way as another way to pinpoint where leaks are coming from. So with the pressure pan, similar way, you depressurize the house to 50 Pascal if you were going to test it. And then you attach your pressure pan to your gauge. If you're using the Retrotec gauge, you would attach it to the blue port. And with your blower door running at 50, there's not really a specific number that you're going to be looking for here. You just want to see if the leaks exist. So for example, if you're trying to find duct leakage with your blower door, you can depressurize the house with your blower door, go around with your pressure pan, and you can check supplies and returns to see if you're getting a big pressure differential between that and the indoor space. So Retrotec makes two different sizes of pressure pan. There's a smaller one that'll fit over most supplies, and there's a much larger one too that'll fit over some return boxes. So if you run your duct tester and you do a duct test and you see that there is leakage, this is a way to kind of pinpoint which branch of it that it's coming from, or whether if it's supply or return. So this is just a quick demo just to kind of show where some of these leaks come from. You pink blobs here are air leakage going into the duct system, and there are spots to see which of these branches are actually leaky. And so as I was talking about with different branches, this is what I wanted to show. And so if you have two different branches coming off of one connection here, so say you test this supply and you get 7.2 Pascal, and you test this one off the same connection and you also get 7.2 Pascal, then your leak is probably coming from this connection since these two are reading the same or similar. So that's just a way that you can pinpoint where that's coming from instead of running your duct tester and then going around aimlessly trying to check all connections. This is a way that you can make it faster. And you can also use pressure pan to find leaks in other places of the envelope too, such as penetrations for light fixtures or bat fans or other electrical penetrations such as receptacles in the wall, especially if you have an attached garage and you want to make sure that they're completely separate. Pressure pan is a good way to go around and check switch boxes and receptacles to see if that wall is actually leaking. So like this is showing here how air leakage behaves in a wall cavity. You can go into one penetration and see if you're having leakage through there or not. So thermal imaging, this is when we get to Jay's part. So Jay, I'm going to, before we do that, Lee, do we have any questions before we go over? We're about halfway through here.
Yeah, there was one asking if we had any advice on testing ceiling-mounted ERVs that have the supply and the return in basically the same space. They're right next to each other. I know we have a reference to it in an older webinar, and I was going to try to find that and email it out, but curious if you have any input.
Yeah, a lot of the ERV manufacturers have a port on there that you can actually hook up a hose to. One thing that you don't want to do, especially with newer ERVs and HRVs, you got to remember that they usually have ECM motors. And so if you block off one side, it's going to ramp that motor up. And then if you have a ramp up to the point where it'll actually shut the system off. And so a lot of manufacturers now are just putting ports on it. So it's good to look at it, try to find whatever the make and the model is, look it up online and see what they model, because they're not all the same. So there's not really a universal answer that'll answer that. It really just depends on which type of ERV or HRV you have.
Okay, great. And I believe that was it for questions.
Okay, cool. Well, Jay, I am going to hand you the wheel here.
All right.
Cool, should be good to go.
All right, thanks, Sam. There we go. So I start out, Sam brought up a number of references to standards and groups that are overseeing this, and what I'll talk about is just a few other standards that come into play for thermal testing and using thermal testing alongside pressure testing. And some of those are on the next slide, but what it does bring up when we start talking about standards and thermography, and especially with thermography, is the certification of thermographers. There is no governing body or reference group that requires thermography of licensing or certification to operate a camera, be that good or be that bad. All we're trying to do is clarify that there is no licensing body that oversees the certification or licensing of thermographers within the United States. Kind of clarifies some of the questions that came from that. The standards that I reference and bring up when I do training is a short list here. The 1186 is air leakage, E779 is the pressure testing standard, and then C1060 is specific to thermographic inspection. But all of them have some reference points when we're doing a full class, and it brings up conditions that need to be done. But the 1189 simply states that pressure differentials of less than 20 pascals can be commonly used to detect air leakage. Now, Sam brought up referencing 50 pascals or minus 50 pascals as a pressure test standard, which is valid. What we're saying here is that if I'm trying to do thermography detection of a leakage point, I can do that with a lot less than 50 pascals. I can do it as low as 5 pascals, and some of the imagery that I have will reinforce that. And why I say, try and do it with less pressure is a typical building wouldn't have a 50 pascal pressure within it or on it, so that if you're trying to find a normal air leak, that would be typical of a 5 PA or a minus 10 PA. And these images simply reference that here's a leak at minus 5, here's that same leak at minus 50, but it doesn't look much different than at minus 25. What can happen is if you're doing a pressure test first in a structure, and then you try and come back to do leak site detection, that you might have some residual pattern from all of this airflow that could obscure and or overemphasize a point that would be misinterpreted. So what I try to teach folks is start at a low pressure for leak detection and only work your way up in pressure to enhance contrast. So again, here's a couple examples of different pressures on a simple exterior wall mounted electrical box. Notice I can see the leak at minus 5. It's overemphasized at minus 50.
Okay, I'm
So
gonna butt in 1 second. I think one thing important to mention is that negative 50 Pascal is like having a 20-mile-an-hour wind hitting all sides of the house at one time. So
very
it's
good.
really, really exaggerated. So I just
It
wanted to
is.
mention that.
Good point, Sam. Thank you. A simple leak detection then that is enhanced by a blower door is to give us that emphasis and that contrast and allow the thermal camera to pick it up as a airflow across the surface. So here we can see airflow underneath this electric baseboard, and we can actually see that the majority of the leak is occurring over here, which would be indicative of a penetration behind that baseboard for the electrical wiring. But when we look at air leakage, we're not just looking at the air leaking into the structure physically as in the previous image. What I can pick up with the thermal camera is this interstitial leakage of airflow on the backside of drywall, for instance, where the air is leaking into the structure but not coming into the living space but moving on the backside of the drywall into another part of the structure. A little bit harder to see on this one, but definitely obvious from a thermal standpoint. Here we can see it a little bit more emphasized, and this is air leakage from an attached porch, and the joists going out of the living space, the cantilever onto the deck, were never air sealed, as Sam explained about air barrier. These were never air sealed. So now with the blower door pulling in a pressure on the structure, it's causing air to leak from the exterior right alongside the joist, and you can see the sides of each joist emphasized by this airflow. So it is giving us airflow, but it's on the backside of the drywall, like I said. So here we have a very common air leakage in an electrical box in the ceiling. Again, like Sam had emphasized early on, that if that box isn't sealed correctly and within the air barrier area of the structure, we're going to get some outside air leaking into this living space through whatever opening they can get, and it's quite common to be electrical penetrations and or plumbing penetrations. We electricians aren't very good at sealing things, so it comes down to we probably cause a lot of that. So here's a blower door set at -10, air leakage around the door. It's a warm area outside compared inside. A typical door is going to have some airflow problems. How bad that's weather stripping, how well the actual door was sealed into the opening, all will be indicated by airflow patterning. Here we have a combination of a number of problems. Here we have the blower door at -15. This is the one we turned it up a little bit just to get the airflow down into these walls. So this area of this particular home is missing a large amount of insulation in the ceiling. It's quite evident in the image here. But what's also showing up is, and again, Sam emphasized in some of the pictures that he had, where the top plate is not sealed correctly, and then we got attic air flowing down into the interior walls, and we can see that patterning quite emphasized with the air being pressurized or negative pressure at -15. Very indicative of interstitial airflow. Another quite common usage of the blower door is in a pre-construction type of testing, and here we have a wall that's insulated. It is not drywalled yet. Tester would come in and test this structure and find these airflow problems long before the drywall is placed on it or the sheetrock, and allows that contractor to fix these problems long before that structure has a problem. It's easier to fix it now than later. So pre-rock sheet inspections are very common now if you're building an energy efficient structure. Sam showed us a picture earlier of a plumbing stack that wasn't sealed through the top plate. And here we have airflow down along that stack through the unsealed area. and the pressure of the door is creating this airflow pattern that kind of reaches down along that stack, and we can definitely pick up those massive types of leaks. Again, this is on the back of the drywall, not on anything inside the building, inside the structure. Here's another one where we have electrical penetrations through the top plate. You can see it's right alongside the stud. Even on this side, the exterior air is coming down through those small penetrations and flowing along the drywall on both sides here, where they've got a hole drilled for the electrical wiring and it wasn't sealed correctly. We also have some airflow along the bottom plate that's not sealed to the subfloor. That's quite common, but we're trying to emphasize this air leakage that can occur and visualize with a thermal camera. Mentioned previously with some HVAC applications, here we have a register or a diffuser placed on the ceiling, and the diffuser is not on right now. It's been shut down so that the pressure testing of the structure can be done. We're not testing the HVAC system at this point. So this airflow that we see is coming in alongside the ductwork and out alongside that diffuser, but that ductwork and the airspace was not sealed correctly in the construction. HVAC folks typically would not caulk that. Again, electrical penetrations, electrical boxes put into the wall, a low voltage penetration. A lot of times these do not have boxes behind these. They might just put in a trim ring, and those are not going to be sealed to the wall. And here we have an electrical box that wasn't sealed at all on the back side. Windows that aren't sealed, of course, behind the trim, airflow is coming around that structure and into the living space. Depending upon how they sealed this, can be indicative of a typical home, but this is actually in an energy efficient home. So the low pressure foam that they used in this case did not fill that space entirely, and it is allowing a little bit of airflow past it. Attic access type of panels or stairs. I've got an example of each. This is just an inset panel laying inside of an edge of trim. They typically wouldn't lay that on any kind of ceiling material, and you can see that quite readily with your camera in that the airflow is coming out of that attic space across this door, and it's also coming out from around the trim into this structure. So we're losing quite a bit of energy through this particular attic access, but they're making up for that loss of energy with an energy efficient bulb. I guess that net zero type of thing. Here we have a pull down set of stairs that one isn't insulated correctly, but we're also getting a little bit of airflow around the ceiling of this door to the framing. Some other applications for thermal imaging goes a little bit beyond pressure testing. Thermal cameras are used quite often in flat roof inspection. It's very difficult on a pitched roof just because of gravity and weepage. But a flat roof, what we're seeing here is the trapped energy that the water would hold versus dry material. Very time specific. There's a good ASTM standard for doing those. Here we have a stucco type of exterior, and it's not sealed in all of these joints, and we're getting some moisture trapped behind that stucco. These are the dark areas here. So we can do some moisture detection on the exterior of a home. Here we have structural block, and moisture within that block has obviously gone with gravity and settled to the lower section of that wall. And another application of concrete masonry block is looking at this wall while it's being built or after it's being built to see if it's structurally sound. And this missing piece that I'm circling with my pointer is a false pilaster that they did not place in when they built this wall. So it's structurally not adequate. It failed. They had to replace that and repair that pilaster. Very doable with a thermal camera. Here we're looking at thermal bridging in a wall. Actually, this has excess framing. It's easier to catch this while they're building the structure, but after the fact, we can come back and say, you know, they've got too many boards here. Maybe in a remodel, you can break that down and save some energy by not having so much thermal bridging. And here's another example of framing from the exterior where we can see a cross brace on this corner of the house. Should be replicated on this corner of the house, but for whatever reason, the carpenter felt it wasn't necessary to go all the way up. So this particular corner is not braced correctly. So we can do a little bit of framing investigation with a thermal camera for construction verification and commissioning. Sam talked about doing some HVAC work with blower doors and pressure pans. I've had the opportunity to do the same with thermal camera, where I can look at diffusers and really decide if this pattern of air coming out is correct for the diffuser. And I've seen patterns of air that come out because of crushed duct, compressed, flexible duct, things like that. And here we've looked at a duct system that's making a transition from a joist enclosed type of duct to a flexible duct. And they put a tie wrap on this flexible duct piece to hold it to this flange. And the last time I checked, tie wraps are not air sealing any kind of gap here. So it's going to show up pretty readily. And here we have one more ventilation issue. Here we're on a ceiling. The duct is a round duct going through a joist cavity from one side to the room to the other. And then we see this large bloom of air spilling onto the backside of the drywall on the ceiling. And that's being caused by ductwork that's not sealed at the joints. And air is pouring out of that duct and actually warming this airspace within the joist cavity. So the air is not getting where it belongs. Radiant heat systems or hydronic heat systems, could be electric. We can look at the patterning, we can look at the flow of fluids and determine if that's all working adequately and warming the space adequately. So I've looked at radiant systems from an efficiency standpoint and a temperature moderation standpoint. What's their recovery time type of thing. So air conditioners fit right into that HVAC. What's that condenser looking like, both visually and thermally? And we can make a correlation to efficiency simply by looking at the thermal picture of this condenser. And if these fins are not clean or combed out correctly, the efficiency of this unit drops considerably and would show up as increased heat at the condenser level. Plumbing systems, both from insulating the pipes, inefficiencies of that, incorrect water temperature settings, I've done that, to plumbing systems for blockage, drain tiles, I've done drain tile blockage type of investigations. Here's a simple P-trap. We can see the water level in the trap and making sure all those things work adequately. Electrical systems, looking at breaker panels, breaker terminations, all of these are very doable in the thermal world. Here we have a simple receptacle with a cord plugged into it, and we have excess of heat at the cord attachment point, which could be a receptacle problem or a cord problem, but very doable with the thermal camera. A little harder to determine on the electrical what's valid or not, because those things get normally warm. Here's a fireplace investigation, a couple different images here. The one on the left is showing a fireplace in a chimney with multiple flues, and the flue liner on this one on the left is broken and allowing the flue gases to get into the actual brickwork. So here we have a major problem in a home where the flue gases are not going out the roof, or out the top of the chimney, I should say, adequately. They're actually spilling into the chimney area itself. Here we have is a fireplace glass, and I was asked to look at this because they felt the manufacturer put the wrong glass in here, and it actually was the wrong glass. It would shatter at high temperatures instead of maintain its integrity. So you got insulation looks, very common with the thermal camera to look at missing insulation. Here you can see that only half of these spaces are actually holding insulation in there. Could be from settling. Most times this is not settling. This is simply just a miss on the insulator's part. Settling usually doesn't come on this far. Settling is usually only in the top couple inches. But here we've got missing insulation within these bays on a warm day. Here we have missing insulation in a simple bay on a cool day. So how that image looks depends upon the daytime temperatures and the differential of temperatures. Also, I get asked, should I be looking at insulation deficiencies from the inside or the outside? I would say your best image is going to come from the inside out, not from the outside in, just because of environmental influences in the exterior of the home. Here we have a couple different door shots. The one on the left is an interior door that's being multi-used as an exterior door now. And it's why you don't use an interior door for an exterior door, is that the interior core is really just corrugated board, and it maintains the laminations on the outside. So this door, you can see all of the patterns of the core. That tells me it's an interior door, and it should not be used as an exterior door. But here's a true exterior door with a side light, and here we've got airflow ceiling problems. We have a door that's not insulated as well as the wall itself, so we're looking at inefficiencies there. Then it leads us to windows. Windows have a number of different factors that can go on with them. We have air leakage on the one on the right. We have airflow across the glass, pretty extensive air leak right there. It's almost a single point air leak. Over on the left side at the very bottom, we can see an airflow pattern up along the glass. This particular glass was set in its frame and not setting caulk. They didn't seal it correctly at all. So that's indicative of that type of problem, manufacturer defect. The gas loss in thermal pane windows, I'm from Wisconsin. We live in the thermal pane window area. This middle pattern that you see on the two top frames, actually a little bit on the lower one here, this is typical of a window that has passed its gas, so to speak, in that the window panes themselves become in a vacuum when the gas leaks out, and the panes bend closer together, which means these get a little bit cooler. But that's also where you're going to see condensation if any air got back into this glass. So the condensation is going to occur on the coldest surfaces. The coldest surfaces are right there in the center. But to answer one of the questions, an exterior view versus an interior view. So here's the same wall from both sides. This interior, we can see where the stud lines are, but we can't see them as clearly as the inside. And part of that reasoning is the exterior wall here is got insulated sheathing on it, and it's actually a reflective sheathing, so that we have less heat transfer on this side of the wall than if on the inside. So here we can see the studs. We can actually see the electrical wires traveling between the wall. So I always recommend on a best day, try and shoot the walls from the inside out. Moisture detection with your camera, it's not a leak detector. I'll never say that a camera is a leak detector. What it can detect is this cooling caused by evaporating moisture. And in this case, we have a wall and moisture in the lower section of this wall. Where it came from is another part of the investigation. How do I tell wall like this isn't just missing insulation? One thing about walls, we can just barely make out the studs on this wall. Moisture doesn't obey framing members. It'll cross over those framing members pretty easily, where insulation tends to stay within the wall cavities themselves. One thing about moisture, when it's wicking into drywall, is a general rule of thumb is 1 inch per hour. So if I have a constant source of water on the floor, this will rise into this drywall 1 inch per hour. So if this is a foot high and I had a constant source of water, I could say this has been wet at least 12 hours. Here we have an active leak on a ceiling from bad roofing material. We actually could hear the water running on the back of this drywall, but thermally it makes a very great definition of what's going on. We're seeing evaporation on the back side of the drywall and very definitive patterns here. Here we have a water spill across the floor on a carpet, actually into the door a little ways, and you can see it into the wall space. So if this needed to be dried, we need to get rid of the carpet. Potentially, you're going to have to open up the wall to let that dry adequately. So back to Sam.
Great, thank you for that, Jay. Lee, do we have any thermal imaging questions?
Yeah, we do. We have one. Kevin was asking, it's one of the earlier slides. He says, doesn't the pre-drywall have to be done with the ceiling drywall installed?
Depends upon how they insulated the ceiling. If it was a foam ceiling where they put in some blocking to hold the foam in place, no. But a lot of times, yes, if it's going with a bad type of insulation or a blown type of insulation that wouldn't be structurally in place, yes, they would typically do a drywall on the ceiling to hold the insulation in place.
Okay, great. Thanks, Jay. I believe that was it.
Okay. And Jay, if you wouldn't mind, we had a couple of good questions on Tuesday about how to purchase a camera, differences between different cameras from the iPhone cameras up to more high dollar ones. Would you mind explaining a little bit more on that?
Oh, sure. That definitely was a question on Tuesday. Some of the lower res cameras, which are typical of the iPhones and the FLIR manufactures a camera called a C2. Those are good cameras, but they don't have the detail or the resolution sufficient to give us good detail on the walls. So if I wanted to image a wall, for instance, I want to see where the stud is in comparison to the rest of the wall. And some of those cameras, one, they don't have a good contrast because the detector is such a low res, but even to get the detail on the wall, you'd have to get so close, you actually couldn't see two stud bays with those cameras from the appropriate distance. So to answer the question more completely is, I get asked a lot in my trainings, which camera should I get? I don't recommend a specific camera so much as try and buy as much detector resolution as you possibly can afford, which means if your budget has enough camera to buy, say, a 320 by 240 detector, and you're going to give up some other features on the camera, that's still a valid buy, because a lot of times the features on the cameras are made up in the software that comes with the cameras themselves. So buy as much detector as, because you can never go wrong with resolution. What you'll sacrifice if you get low resolution is a good contrast and complete detail. So buy as much detector as you possibly can afford is a good way to say that in a few words if possible.
Okay, great. Yeah, thank you, Jay, for that. That was highly informative. I had the pleasure of seeing Jay present at the Energy Out West conference in Phoenix earlier this year, and I definitely learned a lot about thermal imaging that I didn't know. So thanks for joining us twice this week. That was really great.
I look forward to doing some more for you, Sam.
So the majority of this presentation was about the residential industry and how to use blower doors, but there's also a slew of other uses for blower doors as well in the commercial field. And I'm just going to go through a few of them. I'm not going to go in great detail, but basically just introduce them. That way, if you're interested more about it, you can ask us later or do more research on your own. So just going to go through a few more uses of where blower doors are applied. So the first one is pressurized stairwells. So in commercial buildings, especially like the test I did in Richmond, Virginia earlier this year with the big blower door test, it also needed a stairwell pressurization test. And a lot of these times that there's a permanent fan for stairwell pressurization in there. And so to really define where that needs to go or how that needs to perform, you can use a blower door to kind of mimic how that's gonna play out, to see how that stairwell pressurization fan is going to behave. And you can also use it to pressure match that fan to see how much pressure that stairwell pressurization fan is producing. So that's one commercial application for blower doors outside of just doing a blower door test itself. Underfloor access design or raised access flooring. In some commercial buildings, we have this panel flooring that's above what would be the air barrier, or above a channel that would run ductwork or wiring. And so these are pictures from an engineering firm out of Seattle where they did a test on a raised access floor where they actually made their own box and put a blower door fan in it to pressurize it and smoked it. So that way they could see where the leaks were coming from out of the floor. Elevator shaft testing, kind of similar to stairwell pressurization. This is just a write-up on a test that was done in the Bonneville Dam. So basically, they needed to have a pressurization fan in the shaft. They needed to find out where that needed to go, where it would perform the best with different levels. And so you can do that with a blower door. You can simulate how that fan would behave and try it in different areas and until you get it right to see where you need to install that fan. Critical care rooms and medical facilities such as hospitals. So this is really important, especially if you have like quarantine areas, or if you have if you need to put a negative air pressure, that would be like infectious mode, or positive air pressure, which would be protective mode, to really separate two areas out. You would use a blower door to test different rooms to make sure that they're going to be separated from others, and to see how those airflow patterns in the duct system are going to behave. So that's another place where blower doors are used, or in hospitals. Areas of refuge, such as safe rooms. Here's a picture of an oil rig, and then the bottom picture of an oil rig gone bad. So you have workers on there. It's in the middle of the ocean. They have nowhere to go, so you have to have some area of refuge, and it has to be airtight and secluded from any possible danger. And so using a blower door is to make sure that room is going to perform the way it's supposed to. And this is true for other industrial facilities as well. Rain penetration testing is really common in a lot of commercial buildings. Commercial buildings have a lot more going on to them than residential buildings do. And so different assemblies such as windows and doors, they need to make sure that within inclement weather that rain is not going to drive through that assembly. And so you can use a blower door to create a pressure along with a spray rig like the gentleman is using in this picture to see how that's going to perform. Window testing is kind of similar. This is our commercial duct tester here. It's not a blower door, but it's similar to rain penetration testing, where you would do a mock-up test on each individual window assembly to make sure that it's performing the way that it should to keep water out. Roof membrane testing. So you can create a pressure on that roof assembly and smoke it, and will let you see where certain leaks are if they're coming out of the assembly. And you can do the same thing too for before you pour a slab on a building. Like if it's on a contaminated ground, like where a gas station used to be, a lot of times they'll have a membrane over that ground surface, and you can smoke it and pressurize that as well to see if it's going to leak before you pour a slab. Enclosure integrity testing. This is actually a big side of the of Retrotec, where we actually have systems designed just for this. What this refers to is it goes to the fire industry. So in a lot of cases, you have rooms that have items in there that cannot get wet, such as a server room with computer servers inside. So instead of having a water system, you have a dry chemical system. And before you use a blower door, a lot of times you would just have to discharge it to see what would happen. And a lot of times this agent that comes out of this assembly here comes out at such a high pressure that it can be really destructive to what's inside, as well as to the walls and ceiling itself. And so a way to do that is you have to have these walls vented a certain way towards the top, and you can use a blower door to make sure that that agent is going to drop and behave the way it's supposed to without being destructive. And so this is a picture. I'm sure you guys are wondering what's going on here. This is an Air Force base that's housing some fighter jets, and it did not get tested out for its fire system before they loaded everything in there. And so the first time they fired up a jet and rolled it out, it set the fire alarm off, which then dropped this fire suppressant foam down, which then ruined a bunch of jet engines and caused a lot of money worth of damage. So so what happened was they called one of our customers out, and they did some blower door testing to see how to properly ventilate everything to make sure that's not going to happen again. So what you're seeing here, this stuff that looks like clouds, that's actually foam. And then this fire suppressant is stored in tanks, which then goes through piping to serve the room. And so that was just a quick clip of other ways that blower doors are used in the commercial realm outside of residential use. So if you're looking for more, like Lee mentioned earlier, we have a lot of stuff on YouTube from past webinars. And so if you have a specific question, feel free to comb YouTube and see some of the more of our videos. We'll have this one posted up there in a couple of weeks. And so I'd like to give a special thanks to Mr. Jay Bowen for joining us again twice this week to be a part of this. And thank you everybody for attending. Lee, I'm going to ask one more time. Do we have any more questions at the end? Any more come up?
Nope, doesn't look like it.
Okay. Well, great. Then we'll go ahead and wrap it up. Thanks again, everybody, for joining, and we'll see you on the next webinar.